I think we can start the webinar. So welcome to everyone. So this is the webinar associated to the final phase of the Biocomem project. For your info, you all are now mute. But if you have any questions, you can just write them on the chat, and yeah, we will answer when the presentation will be finished. The webinar is recorded, and the video will be available soon, in a couple of days, let's say. And yes, so once again, welcome everyone, and I would give the word to Dr. Oana, that can maybe give a short intro of the project.
Good morning, everybody. Thank you very much for the introduction. So I will share some numbers of the project. Please look. Let me know if you can see the screen.
Yes, we can see the screen.
Thank you very much. So just a few numbers. In terms of money, you can see the contribution from BBI joint GU. This project will finish in a few days at the end of this month. The project starts with monomers, but they actually can be derived from agricultural or bio-waste feedstock. And the objective was to demonstrate that membrane-based separation techniques, especially using this type of PIVA polymers, which are polyether block amide, are more efficient than their heat-based equivalent methods. Because we know that if this happens, this will reduce the overall environmental impact of separation technology in the industry, and this is achieved at different levels by the fact that we use bio-based precursors. It has an impact by other use phase where membrane technology uses less energy than thermal processes, and the fact that we aim to capture carbon dioxide from flue gas streams. Sorry, I'm trying to go to the next slide, and it's not going. Now, so here it's a bit of a map with all the collaborators or the beneficiaries in this project. So we are to higher education, which is University of Maastricht and Eindhoven University. We have two SMEs, Before Plastic and Quantis, two technological centers, Gereon and AS Technalia, and we have a large company, which is Acem. So this is a distribution a bit of all the collaborators. So again, the context and the objectives. We would like to increase the application of membrane-based separation technology in order to decrease the energy consumption, increase the overall sustainability, and reduce the environmental impact of separation processes in the chemical industry, and to develop bio-based gas separation membrane using polyether block amide copolymers. And we are changing their chemistry in this project in order to have them with a higher processability to make monolithic hollow fiber membranes and composite membranes in order to have a higher gas separation performance and to have a higher resistance to chemical attack. So the results you will see later today, how we managed to do this change in chemical structure to improve the PEVA polymers. So how the project was structured, we had like two main blocks. One was material and production scale up, and the other one was prototype membrane module integration and validation. So we started with the core material. We started with bio-based monomers. We didn't synthesize the monomers. We started with them. And then we made the copolymers, and then in Tegnalia and Herion, we worked to make the membranes. And all these activities, obviously between us, we had to collaborate to make process quality control. And then once we had the membranes, we sent the modules to validate the properties at University of Eindhoven, at TRL4, and at DMT for biogas upgrading at TRL5. So this is what we will show today. Transversal activities were related to industrial specification, process design, technical and economical assessment. These were carried out in work package 2 all along the project. At the beginning, obviously, we started with industrial specifications. And then we have, like in all project, dissemination and exploitation plans. And what is very important, we also have recyclability and plastic footprint. And life cycle assessments, which we are now having the final results, and they are very interesting results. So with this, I would like to start showing the results in the webinar today. So please, Luca, take over.
Thank you very much, Oana, for this introduction. Want to remind all the attendees that in case you have any question, you can use the chat. And yeah, with this, I would like to invite our first speaker that will talk about the results of the project, Dr. Katrin Bernertz from University of Maastricht, that will give a presentation on PEBA polymer synthesis pathways to membrane processing. Katrin.
Thank you, Luca. Thank you very much for the kind introduction. Do you see my full screen?
Yes.
Yeah. And this presentation will be given by me, but some parts will be given also by Oana, because this was a very close collaboration. So I will first start with a short introduction. As Oana already said in the introduction, we want to use membranes for gas separation, where we want to, for example, separate flue gas and obtain gas that is rich in carbon dioxide. In terms of membranes, two terms have to be understood. One is the permeability, and that's the rate at which gas permeates through the membrane, and the other is the selectivity, and that's the ability of the membrane to separate the gas molecule from the mixture. I will turn on the pointer. Yes. So different types of membranes for gas separation exist. You have, for example, inorganic, metallic, and polymeric. The inorganics, they can withstand aggressive conditions and high temperatures, but they are very costly, have modest reproducibility, are generally brittle, and show low permeability. The metallic ones are mostly used for hydrogen separation, and also they are associated with a high cost and scalability issues. The polymers are known for their easy processability and easy tunability. And that's why in this project, we will use the polymeric gas separation membranes. Now, if you look to the state of the art, what is typically used in polymeric gas separation membranes is polyethylene glycol or polyethylene oxide. It is especially beneficial for CO2 capture, and this can be explained by dipole interactions between the polyethylene oxide and carbon dioxide. And also, those polymers show a considerable carbon dioxide solubility. And the CO2 selectivity mainly stems from the solubility selectivity. The disadvantages of pure polyethylene glycol-based membranes are that there is a trade-off between permeability and selectivity. Often you have swelling and plasticization, what gives you deterioration of the properties. Also, the polyethylene glycol suffers from aging, and thus also the membrane. There is also limited resistance to fouling, and the mechanical strength is not what it should be because polyethylene oxide is a soft polymer. So various approaches exist to overcome these limitations. One of them is to make block copolymers with other hard segments, and then the PEG is the soft segment, and you combine it with a hard segment that gives you the mechanical properties. Another way used in the literature is blending of low molecular weight PEG with other PEG derivatives, or cross-linking to form a PEG polymer network. In our project, we will focus on the block copolymer strategy, and more specific, we will focus on block copolymers based on polyether and polyamide. They are called polyether block polyamides, or shortly PBAS. And the PBAS belong to the class of the thermoplastic elastomers. Thermoplastic elastomers are characterized by hard and soft segments, and in our case, the polyamide is the hard segment and the polyether the soft segment. And those hard segments, they arrange because there is hydrogen bonding between the amide bonds, and this gives you the mechanical strength of the membrane. And on the other hand, you have the soft segments that, as already explained, thanks to the dipole interactions and the chain mobility, are responsible for the gas separation. Typically, the polyamide segments are semi-crystalline. Now, the issue with commercially available PBAS is that in order to make, for example, monolithic hollow fiber membranes, you need to use a solubilization process, and those polymers are hardly soluble. So we will propose a strategy to tackle this issue. First, I will give you an overview of the process steps from monomer to membrane. So from the monomers, we make at lab scale PBA. That's a task done by us, Maastricht University. Then those PBAs are screened for membrane performance by Technalia, and the best polymers based on the screening results and based on the processability are upscaled, and this upscaling is done by Arkema, and those upscaled polymers are then used for real membrane fabrication by Technalia and Hiraeon. For the PBA synthesis, we use a two-step process. In the first step, we make a polyamide that has carboxylic acid end groups. The polyamide is obtained by combining typically a diacid and a diamine via a polycondensation process. And as Juan already said, we target the use of bio-based building blocks. In the second step, we combine this diacid functionalized polyamide block with a polyether block like polyethylene oxide, and the polyether block is diol functionalized. So we combine acid and alcohol with the formation of an ester link between the amide and the ester blocks. And those blocks are alternating each other. Now, after the PIBA synthesis comes the PIBA screening. And in order to explain this slide, I give the word to Oana.
Yes, thank you very much. So here in this slide, we show how we made this polymer screening. So we wanted to see, first of all, which are the intrinsic gas permeation properties, and also if they have this ability to form an asymmetric structure with a porous substructure. So if we can make a porous film with a top layer that is dense. So in both cases, we had to start with a polymeric solution that was casted on a support using a doctor blade, a casting knife, as in the image in the left. Then to make a homogeneous dense film, we simply evaporated the solvent. In this case was chloroform. And if we wanted to check the ability to form a porous structure by non-solvent induced phase separation, we had to start with a different solution that had NMP as a solvent, normal methylpyrrolidone. And we submerged the wet film in a coagulation bath containing water. And then we got this porous film. So we did these two types of membranes, let's call them like that, to compare the results.
And after this introduction, I want to go to the results we obtained with Biocomem. So, as already mentioned, commercial PIBAs suffer from solubility and thus processability issues, but we are using them as a reference. So we call it in our prototype A. This is a commercial PIBA based on polyamide 11 and polyethylene oxide. And this has a melting point of the PG around 13 degrees and a melting point of the polyamide around 149 degrees. So our approach to improve the solubility is to decrease the crystallinity of the polyamide block. And therefore, we decided to make polyamide based on C10-diamine and furan, which are bio-based building blocks. And of course, the crystallinity is needed for the mechanical properties of the membrane, but the hypothesis is that by using some aromatic groups, we have a way to compensate for the loss in mechanics due to reduced crystallinity. So the first step was to make this prototype B in the two-step route explained in the introduction. So first we make the polyamide and we combine diester of furan, if desired, with a diester of C6 with a diamine C10. And then you see here a notation for the polyamides where the first thing before the point indicates the diamine, and after the point you have the diacid or diester. If there is a slash, it means we made copolymers. So for example, here a copolymer that on one hand contains the C10-diamine combined with furan, and on the other hand, C10-diamine combined with adipic, the ester of adipic acid in a ratio of 60 mole percent to 40 mole percent. This ester functionalized polyamide was then combined with polyethylene glycol and a PIBA was obtained. In the next slide, you see some typical characteristics of PIBAs we made. So we varied the composition, we made pure homopolymers and we made copolymers. And we have also the observation that the molecular weight of the PIBA is relatively low. So we know that we need at least a molecular weight of 40,000, but unfortunately, with this chemistry, we couldn't go to much higher molecular weight than 22,000. And this also results in poor mechanical properties. If we further look, we see that those polymers are characterized by a low TG. That's, by the way, the case for all the PIBAs we made. And we only see a melting point for the PEG. So the polyamide part is not, like we targeted, having reduced crystallinity. It's not showing crystallinity. Then we go to the screening, and Oana will explain the slide about the screening results.
Yes, so we did manage to make some films. Even if they were not mechanically very stable, we could carefully manipulate and characterize them. Once they are placed in the permeation cell, we could make some characterization. So they do have some membrane properties. They have some selectivity, carbon dioxide to nitrogen of 22 and 12. But basically, we could not make porous structure. So these are not useful for membrane applications.
And since they were not useful, we designed another route. So we came with modified prototype B. In this case, we combine a diacid, be it adipic acid or sebacic acid, with a fatty acid diamine to make the polyamide prepolymer. And the reasoning here is, since this fatty acid is in fact a branched structure, we expect that it also helps in reducing crystallinity, but increasing solubility. So this polyamide with acid end groups was then combined with polyethylene oxide to make the PIBA. And what you obtain schematically is shown here. So you have the polyamide with those side chains that are potentially breaking crystallinity. So if we look to the results, the first set of results, there are 3 experiments where we combine the fatty diamine with sebacic acid, and we varied the molecular weight of the polyamide between 1,200 and 3,200, what results in a different weight ratio of polyamide to PEG in the PIBA. We also see that all the polymers have a polyamide melting point and a PEG melting point, where the polyamide melting point is around 100 degrees. That is a good range. Further, we made a variant where we replace sebacic acid, adipic acid with sebacic acid, and we will compare the results. Now, what we observed during the synthesis is that the molecular weight of the PIBA that we obtained is lower than expected because of some sublimation. Nevertheless, we tested the membrane performance, and Oana will explain this slide.
Yeah, so we can see carbon dioxide permeability, which is higher for higher polyether glycol content, at least like the second line. Then the third line is lower, but then the polyamide is different, I think.
And the PEG has a melting point above the testing temperature.
Yes, so it's more crystalline. This is why the permeability is lower. So ideally for these membranes, we should have the melting point for PEG lower than the testing or the application temperature. For carbon dioxide separation and post-combustion processes, it's around from 30 to 50 degrees. It can vary during the year. So yeah, we should have the polyteroxide melting temperature lower than 30 degrees. And anyway, in all these polymers, we were able to make very nice thin films, dense films, to test the intrinsic gas formation properties. But then we didn't manage to make a porous structure in water, but they were interacting too much with water, so these were swelling. So we decided that they cannot be used for NIPS membrane formation.
So, as mentioned, we have problems with the membrane formation, but we also observed sublimation during the synthesis. That's why we decided to slightly change the synthesis route. The composition stays similar, but now instead of using the fatty acid diamine, we use the diacid functionalized fatty acid, and instead of using a small molecule diacid, we use a diamine. So this results then in the acid functionalized polyamide that is again combined with polyethylene oxide to give the PIBA. And the polymers we obtain, first of all, have pretty good molecular weights. And the melting point of the polyamide is around 80 degrees. The melting point of the PEG is below the processing temperature if we use a low molecular weight PEG of 1,500 grams per mole. But when we use a high molecular weight PEG that is also more crystalline of 3,350 grams per mole, the melting point of the PEG is 54 degrees, what is not preferential for the processing. And this is what you also see in the screening results.
Yeah, so once we had these very nice polymers with a higher molecular weight, we tested more than one film for gas formation. This is why you can see plus and minus. This is the standard error. So what we see is that we have a good permeability and that is there. It's comparable between the first two polymers, and the selectivity the same. And then when we have this higher melting point polyether glycol, we have a much lower carbon dioxide permeability. And then with these polymers of higher molecular weight, with the two lines, with the first two polymers, we managed to make nice porous flat sheet films.
So after those lab scale experiments and screening experiments were done, we went to upscaling and we went from tens of grams of polymer to 3 kilograms of polymer, and this is mainly done with Arkema. So we selected those polymers that gave the good membrane formation and good gas separation properties, as well as processability. And also some variations of those polymers were made. So in the first two lines, you see we varied the amount of PEG, so 36% or 45% of PEG. The second block, we made a polyamide 11 and kept with the fatty acid. The third group are copolymers, where we combine the polyamide 11 with the fatty acid as well as the cetanediamine with the fatty acid. And here we studied the influence of the molecular weight of the polyamide, what immediately has an effect on the ratio of polyamide to PEG. So you see we have one polymer with 44% PEG and one with 22% of PEG. And all the polymers have a high melting point for the polyamide and a melting point for the PEG that is below the processing temperature. The screening results are shown on this slide. And we compare it also with some reference polymers.
Okay, so the first line is for polyactive, which is another type of block copolymer that has a polyterglycol part and polybenzene terephthalate part, the other block. And it's used to make thin film composite membrane. So we took these values from carbon dioxide permeability from literature. And then we have the prototype A, which is our reference bio-based PBACs with polyamide 11 as polyamide block. Here we have a higher carbon dioxide permeability, like 3 times higher, at a comparable carbon dioxide to nitrogen selectivity. Then we have this lab scale prototype. I think is the lab scale
Yes.
B1 and B2.
B1 is the lab scale, B2 is upscale, but it has a different composition.
Yes, so for the lab scale, well, the upscaled one, it has a higher carbon dioxide permeability because we have a higher PEG content. And the selectivity, it's also a bit higher. And then we made another, the prototype B3 has a higher PEG content. I will show later why we made this one for processing purposes. And this has even a higher carbon dioxide permeability and much higher carbon dioxide to nitrogen selectivity. So it's already comparable, the selectivity to the benchmark, but the permeability is much higher, which is better. And then we have prototype B4 and B5. Also B4 is a good polymer for carbon dioxide permeability. And B5, we use it as a support porous polymer, and I will show later in hollow fiber processing why it was done that. So it has more polyamide part, and then the permeability for carbon dioxide is lower, but we didn't use it to make a membrane. We use it to make a porous support.
And as you can see, in fact, the overall best polymer is this prototype B3. So from these experiments, we can conclude that the higher PEG content is better for the gas separation properties. And this brings me to the general conclusions. So we successfully synthesized a new class of PIBA for gas separation membranes, which is based on the fatty acids in the polyamide part, and which shows a better processability and solubility for membrane synthesis. And the gas separation properties in the screening results are very promising. So thank you very much for your attention, and the floor is open for discussion.
Yes, thank you very much, Catherine, for this successful story that came out from the Biocomem project. I don't see any questions on the chat. And I can just remind all the attendees that if they have any question, they can just write them there. And I think now we can move to the next presenter. Thanks again, Catherine, for this. And I would give now the word to Dr. Sergei Shishatsky from Herion. I hope I pronounced your name properly. That will give a presentation on thin film composite membrane fabrication.
Yeah, thank you very much, and thank you to Katrina and Oana for the introduction to my talk. So my name is Sergei Shishatsky. I work at Helmholtz-Zentrum Geestart. I will present the work which was mostly done by Angeles Ramirez Cantun, who is a PhD student at our place, but she's on vacation. And of course, with the big help of Dr. Torsten Brinkmann, who is the leader of the engineering department of our institute. So
you are muted. I don't know what happened.
now it works?
Yes.
Yes. Okay, good. I don't know. Strange. Yeah, but so Herion belongs to Helmholtz Association of Research Centers. It's the largest scientific organization in Germany. We have within this structure Forschungszentrum Jülich and DLR, biggest research centers of Germany. And of course, we have DAISY as well. It's electron synchrotron, which is placed not far from us in Hamburg. The Helmholtz-Zentrum Herion is divided into 15 institutes. We have several research programs to get budget funding. And within the Institute of Membrane Research, we have two areas of activity. One area is liquid phase separation, another area is gas phase separation, where I'm employed. And we are doing research from polymer synthesis to pilot scale facilities which we use on industrial sites for separation of industrial gas streams. Our task in Biocomem project was to use the polymer which was developed by our partners, which you have seen and heard just a few minutes ago, to convert it into the membrane and then to convert the membrane into the module, with the aim of post-combustion flue gas treatment, natural gas upgrading, biogas upgrading. So when we get this task, we need to understand where we will put the membrane. What we have something coming into the process and something coming out of the process. So we need to know at which conditions we are getting the mixture from some industrial process, temperature, pressure, composition, impurities, what can kill our membrane, and so on. Then we need conditions this gas stream to the state which is very appropriate for the separation. And then we drive this gas stream through our membrane module, and we get two gas streams. And here we need to know which quality of retentate and permeate we should produce, how much gas we need to extract out of the feed stream, for example, carbon dioxide out of the flue gas, what concentration of carbon dioxide should be in the permeate. And based on this, we decide actually which membrane to take or which material to convert into the membrane. So different types of modules can be used, and you will hear later about hollow fiber membranes. I will not touch it. We are dealing with flat sheet membranes, which can be transferred into the module as a spiral wound or as envelopes. And we are very proud of our envelope type membrane module technology. There are pro and contra for this type of module. So some people say, oh, it's Asian technology, it's very bad membrane area to module to volume ratio. But in this module, we can say what is happening with the membrane at each square centimeter of the membrane. So this is quite nice. And usually we produce quite high performance membranes, and we need really to know what is going on the surface of the membrane, what is concentration polarization, what is the pressure drop inside the module, and so on. So module is, you can see, consists of a lot of envelopes which are accumulated in compartments of different sizes. Size of compartment or number of envelopes inside the compartment depends on how much gas we are pulling out of the feed gas stream. So just to keep the velocity, linear velocity along the membrane element at a constant value in order to provide the best performance of the module. Modules can be of different sizes, so that's a small size here module which we provided for our partners within the project. And standard modules look like this. This is 16 bar module, this is 100 bar module which can be used for natural gas treatment. 16 bar module is used very widely in chemical industry for recovery of volatile organic compounds. So, and this is not the biggest module. So this 30 centimeter module, 31 centimeter module, which can contain up to 70 square meter, it's not the biggest what we can actually do. The biggest which we designed is actually 15,000 square meter. It's the size of a container, 20 feet container. It was invented for gas treatment at power plant to extract carbon dioxide out of the flue gas. And just intermediate stage to this big module is this small module where we tested flow pattern by CFD modeling. So what we can get when we have such big areas of a membrane. So coming finally to the membrane. What are possible morphologies? It's integral asymmetric membrane when all thickness of the membrane is made of one polymer porous part and selective layer. Or thin film composite membrane, where we use relatively cheap materials as a support, and then we deposit on this support several layers of a polymer, each serving specific task. And here you can see that our selective layer is jammed between two layers of polydimethyl siloxane. One is serving as a gutter layer, and if you want, please have a look for the definition of a gutter layer membrane. It was a brilliant patent by Cabasso. I'm not sure, it's in the 80s, I think, when he actually moved the technology to the next modern limit. And the upper layer of PDMS is serving as a protection layer and as a blockage for defects which can occur during formation of a selective layer. So since we have very small amount of polymer deposited on a porous support, we can use basically any material which form a film. And here you can see the variety of applications for which we are using our thin film composite membranes with different selective layers. So it can be glassy polymer, it can be rubbery polymer. Actually, we do mixed matrix membranes. We make immobilized ionic liquid membranes. So everything. And now how to convert the polymer to the CFC membrane? First thing, you need to get a suitable solvent for the polymer. Should be friendly to yourself and to the environment. So you should not die when you use it. It should be volatile, but not too much. So optimum boiling temperature is between 70 and 120 degrees. If it's lower, then you will have very strong cooling of the membrane surface, and you will have a condensation of water from the air. the solvent should dissolve the polymer, so should form a good solution of a polymer. But at concentration of roughly above 5%, it can go into gelation. That's we using sometimes this effect of gelation for production of very tuned membranes for very specific application. Then we need to take appropriate support. Of course, it should be stable against polymer solution. It should have as high surface porosity as possible, stable against the pressure and temperature of the separation process where it should be applied, and suitable for membrane envelope formation by gluing or melting. And on the right, you can see the surface porosity of our standard polyacryl nitrile membrane, which can have surface porosity up to 13%. That's all we can get. That's why it's necessary to have a gutter layer on top of this porous support. Please have a look what is a gutter layer. Then we move to the next step, and we find lowest concentration of a polymer solution where polymer film is formed on top of your support which we are using. Then you deposit this polymer solution on the machine onto the port, you evaporate the solvent, and then you observe nice colors which polymer forms, polymer layer gives you on the surface of the membrane. If you don't see colors, your membrane is too thick or selective layer is too thick. Then you test the membrane and compare results to the properties of polymers, which we have seen in the previous presentation. And you start to repeat everything from, not maybe from the first point, but from this point until you get good agreement between intrinsic property of the polymer and proper gas separation property of the membrane. So how membrane is formed? So at first we need to produce porous support. It's done by a standard solvent-induced or non-solvent-induced phase separation. When you cast a thin layer of a polymer solution onto the non-woven, and then you dive it into the quenching bath, and the phase inversion process occurs, and then you collect it and send it to the post-treatment. Then when you have this support, you start to deposit layers on top of it. For the small lab scale tests, we have a small machine, which is just about 1 meter by 60 centimeters high and 40 centimeters deep. And there, by deep coating process, we are depositing the layer of a polymer. And here we start to understand whether this polymer can be deposited onto the support or it cannot be, and something should be changed. As soon as we start to get a membrane with properties which we consider sufficiently good, we transfer this process to the big machine, to the pilot scale machine, which can produce membranes with 60 centimeter width and up to 250 meters long. And there we are using modified deep coating method when we have two rollers. One is just for guiding of the support. Second roller is for picking up polymer solution from the bath and bringing it into the meniscus. And we are actually pulling the polymer solution selective layer out of this meniscus. And the processes which are occurring in this meniscus are described by very complicated mathematics. I will not go into this. And you can see it if you want in the publication of Florian Brennecke and Julia Klot, which was published in 2021. Then you finally get your membrane. It's a roll of approximately 250 meters. Along the membrane production process, you can take stamps. You can just cut pieces of the membrane and have a stack of them. Then you send this roll of membrane to the storage, and then you start to investigate internal morphology of the membrane and gas transport properties. So you can see here examples of two membranes which were developed within the Biocomem project of prototype A and prototype A1 polymers. And you can see that we achieved in first case thickness of roughly 80 nanometers. And in the next case, we decided to increase the thickness to 150 nanometers due to some interesting effects which we observed during production of the first prototype A membrane. 80 nanometers mean that you need just 80 milligram of polymer per square meter of membrane. It means that you can use basically any polymer you can find for production of a membrane which can be tested at real industrial conditions. Because 2 grams of membrane is enough for production of 20 square meters of membrane, and that's already a good module to be placed into some industrial environment. So this is very big benefit of thin film composite membrane ideology, let's say. So then when we are satisfied how the membrane look in an electron microscope, we go for testing, or actually it's mixed between electron microscopy and testing, always, because electron microscopy takes time. And we place the membrane into so-called pressure increase facility, where we can investigate permeation of different gases, up to 15 gases and one vapor, through our membrane in a temperature range from 1 degree to 120 degree, and with a feed pressure up to 1,200 millibar. We don't go to higher pressures on this type of facility because then gases start to be non-ideal. We need to take into account real terms applied to description of the gas transport property. And we collect the data. And here we see the table of properties of membranes which were produced within Biocomem project. And you can see that we can have up to 2000 GPU, or about 5.5 cubic meters per square meter hour bar of a carbon dioxide with selectivity, so 31, 34, 30. Not too high selectivity, I should say, but for the first stage of gas separation, or for the flue gas, that's quite good. For the first stage, we need a permeance. Engineers tell, just give me permeance, because permeance mean investment, how much membrane you need to put into the process. For the second stage, it's better to use membrane with a somewhat higher selectivity. So, of course, since we took a lot of samples, we do screening of the membrane quality along the membrane length of this roll, which you have seen before. And here you can see data for nitrogen, methane, and carbon dioxide for two prototype A and A1. And you can see that actually the membrane quality is not changing significantly along the length of the membrane. This is quite nice to know. And then we come to conversion of the membrane into membrane envelopes. This is very labor intensive because we need to cut a lot. We need to weld each envelope, and you need to take it into hands, so it's a labor cost. You need to cut it after the membrane envelope is formed. You can need to cut it to the shape which is suitable for the module. Then you need to test it with oxygen, nitrogen for the quality of the envelope, and then you finally put it into the stack. And you collect the data for each envelope, and then you use this data to model the module. Here you see results of testing of envelopes in respect to the number of envelope, and this number of envelope is related to the position of the envelope along the membrane which was produced. And you can see that for prototype A and A1, the selectivity for oxygen nitrogen was quite constant. In case of prototype A1, the permeance of nitrogen jumped. I think it's due to change of the speed of one roller. And then it slightly decayed to the end. That's most probably due to evaporation of a solvent from this bus from which a roller picks up polymer solution. And so we get a thicker layer. And as comparison, you have properties of a polyactive membrane. Our standard membrane, which we try to put into the practical application. What you can see here, permeance for nitrogen is 0.0660 liters of nitrogen per square meter. For prototype A, we have 150 liters, so it's 2.5 times faster than polyactive. And for prototype A1, which was twice thicker, we have roughly 75 liters per square meter hour bar, which corresponds to the thickness observed in ACM image. That's a good indication, because then we have two proofs of membrane quality by electron microscopy and corresponding value from envelope investigation. Oxygen nitrogen we use because we just press air through the membrane, and then we observe what concentration of oxygen is on the permeate side. And this is first real exposure of the membrane to the mixed gas feed stream. And we can judge from this investigation what is the membrane quality. This is quite a good number. Then we test it as well for the module. And when we are finished with this, we give it to module formation. We model the module according to properties of each envelope which we want to put into the module. We calculate what we can get when we have a feed stream of a certain linear, so certain volumetric velocity, and we calculate what is the linear velocity along the envelope, how many envelopes should be in each compartment, according to the feed stream which is coming into the module. And then we test this module performance on our machines. We compare the data which we get from experiment to the data to the module, and we finally deliver it to our partners in Biocomem. And we delivered at least one or maybe even two modules to our partners. And so I come into conclusions. So first of all, separation processes based on polymeric membranes are highly accepted by industry, but polymeric membrane is not ultimate solution. It has a selectivity. So it's always something is coming together with the carbon dioxide through the membrane. And in flue gas separation, the biggest problem is oxygen, because you get accumulation of oxygen on the permeate side, and that's a big problem. You need to know it. So it's always nice to combine membrane separation stage with another method like adsorption, or whatever you can find. And then it works perfectly. Multi-layer design of membranes gives huge flexibility for developer how to make the membrane. You can use experimental materials for piloting at industrial conditions. And this new generation of membranes which were development gives the possibility to use this bio-PEBA polymers and other polymers which will be synthesized further for practical application. And with this, I thank you for your attention.
Thank you very much, Sergey, for this very interesting presentation about converting polymers to membranes. And, again, I want to ask from the attendees if there are any questions, and I don't see any on the chat. And looking also at the timing and sticking to the agenda, I would then say thank you, Sergey, and I will move to. Thanks. I will move to the next presenter, who is again Dr. Oana David from Tecnalia. And Oana will give a speech on hollow fiber membrane fabrication.
Thank you very much. So I will share my screen. Just a moment. Not this one. Okay, I suppose that you can see it. Yes. So I will show
Yes.
the work we are doing in Tecnalia for hollow fiber membrane fabrication. Here we are two people which we are leading this kind of developments. Is me and Miran Echeverria. Well, as a general introduction, I would like to highlight the motivation behind membrane technology, and is mostly related to the energy consumption. So in the graphical representation at the left, you can see that at least in US, the chemical industry, half of what chemical industry consumes in terms of energy is related to membrane, to separation processes. Most of them are thermally driven. These are distillation, drying, and evaporation. So it is calculated that if we would replace this thermally driven separation with membranes, 90% of less energy would be used. And this is because membrane separation does not require a gas-liquid phase change. And they also have the advantage that they have a smaller separation units, have lack of mechanical complexity, and they can operate under continuous and steady state conditions. So the gas separation membranes, we can classify them according to the applications or the type of membrane. We have carbon dioxide capture. So this is carbon dioxide separation from nitrogen in flue gases that we already discussed today. We can also have carbon methane purification from natural gas or biogas, hydrogen purification, and olefin and paraffin separation in different streams from chemical industry, and also water vapor separation in the dehydration processes. And the types of membrane can be classified according to the material, the structure, and geometry. So thank you, Catherine, for showing a bit some differences in types of in terms of materials. And I would like to go more into details now in structure and geometry. So as it was already said today, the structure can be either symmetric and asymmetric. And the geometry can be either flat sheet, tubular, and if these tubes have an outer diameter lower than 0.5 millimeters, they are called hollow fibers. So more into detail, we always make a homogeneous dense film in order to characterize the intrinsic gas permeation properties, as we already showed today. These are done either by the extrusion of a polymeric melt or by evaporation of a solution, a polymeric solution, which was disposed as a film on a support. And here the term of phase inversion is related to the fact that the polymer from a fluid state, it goes into a solid state. When we make asymmetric structure, we basically make them because we want for the dense part, the one that is doing actually the separated, to be as thin as possible. So we need to have, as Helen showed before, this very thin layer and a porous support. So we can make a monolithic structure, which means that we make both parts at the same time from the same material, the same polymer, or we can make a composite structure as it was shown before by Heron. So I will not go into details, but I will go into details on hollow fiber spinning, and this is what we are doing at Tecnalia. So this is a monolithic structure, so it's integrally made from the same material. Here the selective and dense layer is at the outside. It can also be named as a skin. And both parts are made at the same time. As I previously said, we have a porous part, and these pores from the porous part are gradually becoming smaller from the inner side to the outer side. And finally, we don't have any pores. I mean, the gas is then diffused through the molecular space between the polymeric chain. In the end, here is a module. We place these fibers that we have in the image in the left inside the permeation module, which is tubular as well. And the blue color here represents the resin we use to seal the inner side from the outer side of the membrane to create a space for the feed and a space to collect the permeate. This is an example of a prototype module we can do at Tecnalia. So the motivation to go to such small fibers is related to how much membrane area we can pack inside a separation module. And here it's a simple calculation. We have the diameter of the hollow fiber. We consider that the surface area on the outside is where the membrane is. And we also consider that we can pack about 50% of the inner volume with these fibers. So we made a simple calculation, and we can see that if these fibers, so when the tubes have an outer diameter lower than 0.5, we have an exponential increase in the packing density. So this is the advantage of the hollow fiber membranes. So it's 10 times higher than plate and frame modules, and the advantages of plate and frame modules were shown before by Heron. But also these small capillaries can hand up normally high transmembrane pressure differences up to 70 bars. And because both layers are made at the same time, because of this monolithic structure, we assume we know that the fabrication costs are lower. So we only have one process to make monolithic hollow fiber membranes, and this is the spinning process. So here I very simply show how it's done. We have a polymeric solution that is co-extruded through a spinneret with a bore liquid. The cross-section of the spinneret is shown now. What we have here at the exit of the spinneret, it's a hollow tube. So this is a polymeric solution in this shape. And we managed to maintain the hole by having a bore liquid that contains a mixture of water and the solvent. And then we have a phase or not. Before coagulating this structure in a water bath, we can have an air gap where some solvent evaporation on the outside can take place, and I will show later why. Yes, so we have many process parameters that we need to control and optimize in order to achieve this nice structure we have here as an example in the picture. And sometimes we can place nitrogen outside to promote solvent evaporation on the outside in the air gap to achieve this densification of the polymer before coagulation in the water bath where the porous substructure is formed. So this is the classical way for gas separation membranes. As I said, we have a nitrogen stream outside, inert gas, and for the bore liquid, we have water mixed with NMP. So then we form the selective layer outside. We can also have the selective layer inside, and here it is represented in the second part, in the right side of the slide. In this case, we have water in as coagulation liquid that can mix. The condition is for the water to mix very well with a solvent that is used for the polymeric solution. And then outside we have humidity. So here we would like to have an outer surface with a high porosity and an inner surface with a dense layer. So when we decide to develop new hollow fiber membranes, we first start with the process, and according to the application, we need to define what are the performance these membranes would need to have at the end. Based on this, we develop or we select a material for this and we check their properties. So we prepare a dense film and we characterize. This is already shown in Biocomem how we did it. And then if we don't like, we make more synthesis for the polymer. When we finally decide that it's worth it, we start making hollow fiber membranes. So we need to make many experiments in order to optimize the structure. If we cannot optimize at all, we have to go back to material screening or development. When we are finally happy, we try to scale up and to make a prototype. So the benchmark, all the normal polymers that can be used for spinning for this thread formation are limited. It's not like we can use any polymer. So this is a list of polymer that usually have this thread forming ability. And we have many polyimides like P84, PBI, 6-FDA DAM, and polyimide XTEM. And at Tecnalia, we already have nice recipes to work with these polyimides. And now I will start showing some results we have in Biocomem project. So I start, why we use PIBA type polymers was very nicely shown before, so I will not show again, but in this kind of graphical representation, you can see that these block copolymers can form domains of polyether oxide flexible network where carbon dioxide permeation is preferred, and then we have the polyamide part that is making a reinforcement of the polyether oxide flexible network. So this is the benchmark. Before we started the project, we have different paybacks with their properties in terms of permeability for carbon dioxide. They are very good for carbon dioxide separation from nitrogen, and in comparison with polyimides, they are not so good for carbon dioxide separation from methane. It's also very interesting to highlight that they are reverse selective towards hydrogen. So carbon dioxide goes faster than hydrogen, even if hydrogen is smaller. And this is because of the high solubility of carbon dioxide into the polyether oxide part. And then when we started the project, we decided to actually work more with these polymers because we observed in a project before that we have these PBACs with polyamide 11, which is bio-based, is coming from castor oil. We have observed that has a much higher carbon dioxide permeability. So we decided, here I'm showing also polyactive as we showed before. So we decided then that is interesting to work with this polymer. So we had the first research line trying to make composite membranes. And these are the flat sheet membranes that Herion showed before. And then we wanted to change the polyamide chemistry to be able to make PIBA monolithic hollow fiber membranes. And in this case, for this research line, we kept the polyether oxide chemistry fossil fuel based. We kept it constant. And then finally, we also wanted to try to make a fully bio-based material to have polyether oxide and polyamide part bio-based. And at the end, we were thinking that we will check if we can make hollow fiber membranes monolithic, or we need to make a coating procedure. So here is 35B6, this polymer here. is the one that was synthesized by University of Maastricht at lab scale. It's the one we, based on flat sheet NIPS process and gas formation results, we decided that it might be the best to scale up. But before we actually said to Arkema to scale it up, we wanted to check if we can actually make a hollow fiber. We had some polymers and we can make some a small spinning experiment with not so much quantity of polymer. And before doing that, we needed to know what would be a good polymeric solution formulation for a spinning experiment. So here at the left side, these are the components that a spinning solution can have. We have the polymer, we have the solvent, which is normal methyl pyrrolidone, and then we can have different additives with different purposes. So lithium chloride, it's a salt of very small size that is acting as a separator, so it can disrupt the hydrogen bonds between the polyamide chains that are formed there, and then it can help dissolve the polymer basically and prevent gel formation. This is what we knew already from the literature, and it's additive we normally use for polybenzimidazole. Then we can have PVP, which is polyvinylidene pyrrolidone. It's an additive of low molecular weight. This is 30,000 gram per mole that can dissolve in water after spinning when we wash the fibers. So its main purpose, it has two purposes: to increase the solution viscosity, then we can form a stable thread, and also because we can wash it from the polymer, from the coagulated polymer at the end, it can promote pore formation. It can have bigger pores. And then we sometimes we add another solvent, which is THF. This is tetrahydrofuran that has a very much lower boiling point than NMP. So it can evaporate. And if we want to make the selective layer out at the outside, we can densify we can increase the polymer concentration at the outside part of the fiber by evaporating faster the solvent, this THF part. So then we wanted to see if we made solutions with the polymer and the solvent and or not one of the additives, and these are solutions 1 to 4. And then we made combinations of two additives, and at the end, all of the additives in this concentration I'm showing here. So what we observed that if we mix the polymer with a solvent alone, we cannot dissolve it, and the solution that we form is not homogeneous, so it doesn't work. If we add lithium chloride, yes, we make a homogeneous fluid solution. If we don't have lithium chloride and we have PVP, then we sort of dissolve the polymer, but the final solution is not homogeneous. And if we don't have lithium chloride, but we have THF, we do form a nice solution. So this means that THF is a better solvent than NMP for this polymer. Then going to more complex solutions, all that had PVP are not homogeneous. So basically, we cannot mix these two polymers together. So this we decided that PVP as an additive is not good. We cannot add it. And then we decided like the best formulation is having the polymer, the solvent, lithium chloride, and or not THF as an additive. We also observed that these solutions are liquid at 40 degrees, but at room temperature, they make a gel. So based on this, we kind of realized that we need to make spinning at 40 or higher temperatures. So we did a few spinning experiments with this lab scale batch. And with these first results, we realized that we can make hollow fibers, and we can make the selective layer either inside or outside. So with these results, we decided that we should scale up this polymer. These are a few SEM images of these first results. They do not have an optimized structure, but we did have some porosity in the middle side of the fibers. At the inner side, we have a dense layer, and at the surface, at the outer side, well, the porosity, we should have a very nice porous layer, but these were the first experiments, so with a lab scale batch. So we decided to scale up this polymer. Arkema did a scale up. Here I'm showing again the permeation results that were shown before by Katrin, the University of Maastricht. So there are two. We have this batch at lab scale MS 2001-35, and then it was scaled up in two different polymers. With the only difference between them was a bit the polyamide to polyteroxide ratio, but it is the same chemistry. And with these ones, we started to make hollow fiber membranes, and we did. And we, based on these results, we also can estimate if we make the hollow fiber membrane with the optimal structure I showed before, which would be the properties for gas permeation we would be able to achieve. So it's like about 1,000 GPUs and selectivity carbon dioxide to nitrogen of 30. With dense sheet films of these polymers, we double check their gas permeation properties also by varying the feed pressure. So here we went up to pressure of 40 bars. Well, we see that there is an increase in carbon dioxide permeability, reaching values of more than 500 bar. And the other gases are more or less, they have a constant permeability. This is why the selectivity of carbon dioxide to nitrogen and to the other gases increases with pressure, but increases more for carbon dioxide to nitrogen, and we reach values of about 50, which is very nice. So then we started with the scale-up polymers. They were at 10 kilogram scale. We started to do a study what concentrations of this polymer we should use in the spinning solutions, because we need to form this stable thread. There is a minimum concentration that we need to use for this thread to maintain itself in the air gap. And this is determined based on this kind of graphical representation where we have different concentration, and we check from which point the viscosity starts to increase exponentially. We have determined that the good concentration is about 30%. Nevertheless, we did many spinning experiments at lower concentrations because they are semi-crystalline polymers. We play also with gel formation during the spinning experiment, and we do manage with low viscosity thread to form a stable thread, because at the same time in the air gap we can have gel formation. So we managed to do finally a very nice. So here at the image in the right, you can see the cross section of the fibers wet in water. They were very nice, but when we dried them, the porous collapse and structure collapse because the polyteroxide, because they are too flexible, basically. So here I show some gas permeation results. When we dry the fibers directly from water, we managed to sometimes to achieve good selectivities of 30-35 at very low permeabilities. And because we basically achieved dense tubes, the porous structure collapsed. When we dried them by freeze drying, we did manage to keep pores open, but they were defective. So, and on top of all, it was it was not, they could not be well manipulated while dried. They could not stand up to pressure differences. So we decided to go to a different approach. So again, going back to the spinning experiments, instead of doing one layer spinning, we decided to do 2-layer spinning. So in this case, we form the 2 layers at the same time. It's not a coating process. It's still a non-solvent induced phase separation process of the 2 layers at the same time. But we can use a P-Box polymer with the same chemistry in the both layers, but with more polyamide part in the supporting layer in order to prevent pore collapsing due to high flexibility of the polymer chain. And then we have Arkema scaled up 2 new polymers. The second TLT 550 was the one that was for the super layer, had more polyamide part. And TLT 549 was even with an even higher polytrioxide part, so it even had higher gas permeability to carbon dioxide. So with these values, we assume that if we have this dual layer hollow fiber approach, we can achieve a selective layer, a thick one of about 1 micrometer, because the entire layer made with this polymer the pore structure that can form by NIPS process will collapse into a dense layer, but the pore structure made with 550 will maintain open. So we assume this kind of values of 400 GPUs and selectivity of carbon dioxide to nitrogen of 30 can be achieved. And then I show a spinning experiments where we change a few parameters during the spinning session. First of all, we change the temperature in the bed. We made 3 experiments at 20 degrees temperature in the coagulation bed and 2 other experiments at 40 degrees. And then we check air gap of 10 and 1.5 centimeters and the take-up rate at 5, 10, and 8. So dimensionally, we can see that both the outer and the inner diameter, obviously they increase with increasing the take-up rate, and it doesn't matter at which air gap height you work and at which quench bath temperature. And then we also checked gas permeation of these membranes. So the membranes that were done at a higher quench bath coagulation temperature have a much higher carbon dioxide permeability, and the membranes that were done at a higher take-up rate are somehow they have a higher selectivity. So we can see how spinning process parameters can influence gas permeation properties and the final properties of the membrane. These are the membranes made with a SEM micrograph. So we see the inner layer dense. This is the selective part. And this is the porous part of the outer layer. And we try to determine the porosity in the cross section, which was about 45% if we take the entire cross section. Here we have these big pores which are not desired, so we still have to improve that part of the fibers. And then if we look here at this nice part, we would like to have this kind of interconnected pores all over the cross section. Then here we have a porosity of 35%, and this is done by image analysis. If we look at the outer surface, here we would like to have a porous outer surface, and we still have to improve that. But it's very difficult based on images to compare the fibers between them, and making this kind of image evaluation to check the porosity, it's also difficult here. We checked mechanical properties. We made elongation tests. And as you can see, elongation at break is very high. They are very, very flexible. So they are like a gum. Is much higher than the benchmark, which you can see here at the bottom. And then the ultimate strength it's low. It's more or less comparable to polytersulfone 28 fibers. And like sort of conclusion, we still need to optimize a bit hollow fiber membrane fabrication. It seems that a dual layer approach, it works. We will need to increase the surface porosity to eliminate these macro voids we saw because they give low stability to pressure, and to achieve better selectivity, to densify better the inner layer. And then we already, even if we didn't had an optimized recipe, we did a few scale-up experiments. And like in 4 scale-ups experiments, we managed also to achieve a successful scale-up. So thank you very much for your attention, and please let me know if you have any questions.
Thank you very much, Joanna. Maybe yeah, I have a question. It's actually regarding the upscale part, and how do you see this upscale for the hollow fiber type, like the path towards industry for this application?
Yeah. So what we need to do is freeze drying to keep the pores open. Even if we increase the polyamide concentration in the support layer, we still need to do freeze drying. We were trying to see other drying methods, but they do not work. So this freeze drying, it's more energy intensive. And in the LCA we did. So first of all, it is possible industrially. So people do freeze drying industrially. We already checked equipments for that if they exist. So it is possible. And then secondly, we did the life cycle assessment already, and we wanted to check if this it's doable, like from energy point of view. And the results are that more or less the operating costs are the ones that use more energy, much more than the fabrication cost of the membranes.
Okay.
So it doesn't have so much impact in the end.
Okay.
Because
Okay.
you have a product that is supposed to last for 5 years. So it's always the application, the operating, that can be more energy intensive than the production.
Thank you very much for your nice presentation. And then I will move to the next speaker. I see Dr. Rusbe Ramezani from Technical University Eindhoven, which is ready, and he will speak about membrane-based process design and economics. Rusbe, the floor is yours.
Thank you very much, Luca, for introduction. I'm going to share my slides. So can you see?
Yes.
Awesome. Okay, thanks again, Luca, and good morning, and welcome everyone for joining our final webinar in Biocomem project. So I'm going to spend next 20 minutes describing briefly some work that I did in Biocomem project. So far, thanks to our previous speaker, you know what are the objectives of this project and how we fabricated the membrane for gas separation applications. So the next step would be to test feasibility of fabricated Biocomem membrane for real industrial application. So what I did is techno-economic assessment of the Biocomem membrane at 3 gas separation applications, including post-combustion CO2 capture, natural gas, and biogas upgrade, to see how this membrane work at the real industrial application from a cost point of view, how much energy we need, how much is going to be the membrane area, and go on. So as you all know, the efficiency of your process, membrane-based gas separation technology, strongly depends to performance of your membrane. So we do our best to improve, to fabricate membrane with higher membrane selectivity and permeability. But there is a limitation to improve both of them to reduce at the end gas separation cost. So the alternative solution would be to design a cost-effective process for your separation, so gas separation, technology. So what we did here is to start with designing the new process for our application and try to optimize it to minimize the gas separation cost. So to do that, first of all, you need to know for which application you are going to design your process. So based on that application, of course, you know your inlet gas specification, including your gas mixture composition, flow rate, temperature, pressure. So then also you need to know your product separation target, purity, recovery. Then you choose your membrane, depends on that your application. Then another important is to select the number of stages you need to achieve your target, right? So at the end, you start optimizing and go to next step would be the economic assessment. So let's start with the simple one. Basically, to separate your gas, whatever is going to be the CO2 nitrogen or CO2 methane or hydrogen separation for any application, the simple one is going to be you have one membrane stage. Of course, you have inlet gas flow going to passing the first compressor to provide you enough driving force. You have heat exchanger to reduce temperature before sending to membrane stage. You have permeate and retention inside. So it depends which application you have. Your product can be in the retention side, like for methane, for biogas, natural gas application, or CO2, purity CO2 in permeate side, for example, for post-combustion CO2 capture. Of course, you can have vacuum pump in the permeate side to provide even more driving force for that. But the big problem for this structure, this design or configuration is, for example, in the case of the CO2 nitrogen separation, specifically the polymer membrane, you need a membrane with over 200 membrane selectivity. But at the moment, the selectivity for this gas mixture is about 45, 50 in the literature. So you cannot reach with one membrane stage to high purity and recovery. So what can you do is, okay, to add another membrane stage. So it could be 2 membrane stages. So you see here 2 different configurations is for different applications. You can rotate, you can recycle retention side or permeate side, depends which application you are using. And you can play with this structure, add more compressor, more recycle stream. But again, you cannot sometimes reach to high purity recovery with 2 stages, and that configuration you can optimize your own structure, but it doesn't mean your configuration is the best one or is the optimal structure. So you can keep going that and add 3 stages, 4 stages to reach your objective. Of course, you can reach your objectives, but you need to identify the best configuration for your application as the minimum cost. So, for example, here we'll show you the configuration with 3 stages. So here you can see many different configuration or structure you can design only with 3 stages. Here you have, as an example, 4 different configuration. It could be much more than this. You can design your own 3 stages, add this strip to that stage, recycle that one, and then you can start optimize your own configuration. But that doesn't mean, as I wrote in this slide, it doesn't mean your configuration is in the optimal structure for achieving your separation target at the minimum cost. So what we did at TUI is we start with designing the new multi-stage membrane, superstructure membrane. As you can see, we designed the superstructure with 3 membrane. So that is actually the heart of this process. Here we have 3 membrane stages, and the benefit of this superstructure is we don't design configuration for any application or any separation target. We let the software to start with the superstructure, then to reach the optimal configuration depends to application we have, depends to separation we need to achieve, right? So the software start with the superstructure, so it depends to our application. Maybe at the end it give us 2 stages, maybe it give us 3 stages, or even 1. Okay, let's see how it look like after optimization, starting with the basic superstructure. So talking about superstructure, as I said, we have 3 main stage, and also we have 4 compressor. Keep in mind, this is a structure for post-combustion CO2 capture. General is the same for all 3 applications, also natural gas and biogas, but there are some minor change between the structure. For example, in the case of the post-combustion, you need a final compressor to increase your pressure of your CO2 to 76 bar, and at the end you need to have another pump to increase to 150 bar to liquefy your carbon dioxide for the next step. Also, in the retention side, when you are going to optimize for natural and biogas, your methane would be in the retention side. So depends to which pressure you need in the grid, you need to have expander or compressor. So that's the minor difference between the 3 applications. But at the end, the general is the same. Here, of course, I explained about expander, and also we have 3 vacuum pump we added in the permeate side of each stage. We optimize each one separately between 0.2 bar and 1 bar to give us even more driving force. And that's the new one. Sometimes you don't see in the literature for natural gas and biogas to put the vacuum pump the permeate side. And so the main part are membrane, the compressor, the expander, and the vacuum pump. But also we put many splitter and mixer. This gives the software flexibility to investigate many various configurations to finally to identify the best configuration according to our applications. So here you see we have about 5 mixer and 7 splitters. So how it works? We define, as I explain later, as a decision variable, we define the lower and upper bound for each variable. If the stream go to any membrane stages has 0 failure rate or very low failure rate, it means you can ignore that stage. So it could be membrane stage number 1, 2, or even 3. And at the end, your superstructure become much more simpler and even maybe became 2 stages. So I will show you how it works later in the different applications. So the next step would be you select your configuration, flow configuration. In this case, we start with the co-current flow. Then you need to choose your simulation tools. Here we use the combination of the Aspen Plus and Aspen Custom Modeler. So in Aspen Plus, you have all equipment you need for designing this structure, except the membrane module. So you need to we use the Aspen Custom Modeler. We use the Fortran language to write out the mass transfer model. And after that, you can implement the Aspen, the memory module in the Aspen Plus. And the next one is now you designed your superstructure. you have your membrane module simulate in your Raspberry Plus, then you need to identify your economic model. And for that one, you need to write the code for Apex and Copex. So here we did for all three applications. Here you can see the main item which is affect our cost is the cost for membrane module, the compressor, vacuum pump, expander. So based on that one, you need to calculate the CAPEX and OPEX. And we usually ignore the price for mixer and the splitter, their price compared to huge cost of their power or utilities is nothing. So we usually ignore that. And you, at the end, you can calculate your gas processing cost. So keep in mind, the equation you see here is for post-combustion CO2 capture. For natural gas and biogas, the equation is a bit different. You need to also consider the price of the methane. So you have your superstructure, you define the economic model, then you need to start optimize your superstructure based on your application you have. So what you have is, you know, your input variable, you know, you have your inlet gas condition. You know your membrane selectivity and gas permeance. You know what pressure you want to reach, and you have you know your separation target. What's going to be your methane purity or recovery, or even carbon dioxide methane or recovery. So and that one also, of course, you define your target, and to reach that you need to have you need to also define your decision variable. In this case, it would be the membrane area for each stage. You have 3 stages here. Also, you have the pressure for retention side. It's going to be the operating pressure. In this case, we assume it's going to be constant at all the process. Also, pressure for permeate side of each stage separately. And also, you have about 7 split fraction, which gives you more flexibility to investigate various configuration. And at the end, as a result, you will find how many membrane stages you need for your application, what is going to be your CAPEX, OPEX, how much membrane area you need to achieve your separation, how much power you need, and all this information. So let's start with first application, which is post-combustion CO2 capture. So we did the optimization and economic assessment for all 3 applications at different separation target, different conditions. We also did sensitive analysis, right? But as a limited time, cannot show all the structure. But for each application, I show you one structure as example, and we go to detail, we discuss. So here you see the table. Thanks to our previous speaker, you know what is the selectivity and permeance for prototype A and A1. Prototype A1 has a bit better membrane selectivity compared to prototype A. I did all this process for also 2 different membranes to see how membrane property affects gas separation cost, energy consumption, membrane area. We will discuss later in the result section. So let's start with the first application. We need to achieve, for post-combustion, we consider a mixture of the carbon dioxide, nitrogen. Of course, you have more impurity, but in this case, only CO2 and nitrogen. We're going to reach to 90% recovery and 95% purity, right? So in the green color, you see what information we have: the inlet gas flow, the product pressure, and the product our separation target. So we start with the superstructure. We give it to software. We define all the optimization strategy. We define all the economic model, and at the end, it gives us this result. For post-combustion CO2 capture, we need 3 membrane stages to reach our separation target, right? So the amount of area you can see at the end, the cost, gas processing cost is going to be about 46 euro per ton of carbon dioxide capture. Also, you can see the specific energy consumption. So all the information you have, the membrane area for each stage, the amount of power you need for all the structure. So except the, not only you optimize all these parameters, but also you are optimize your structure. So you can, it's obvious you can see the inlet flow gas is the best configuration is we send the flow gas to the second membrane stage with mix of the permeate from the first membrane stage and the recycled stream which coming from the third membrane stage. And of course, the retain data of the second one goes to the third one and the rest. Also, we need 2 vacuum pump for the second and the third membrane stages. But the first one we don't need because at the end the pressure was the 1 bar, so we ignore it. And the all information, the rest you can see here. And based on that one, you can calculate the gas separation cost, the capex, opex. Also, we did this optimization for different membrane properties, also for different separation target. So that one is for Porty.A1, which is the best membrane in this case, with a higher membrane selectivity. Here in this table, you can see the result of 2 different membrane with 2 different membrane properties, selectivity and permeance, and also at 3 different separation targets. So obviously you can see how separation target can affect gas separation cost and also energy consumption, the amount of the power change, amount of the membrane area. So it's obviously, you see how gas separation cost strongly depends to your membrane property. So for example, only with a bit improvement in the membrane selectivity, you can reduce your gas separation cost, for example, from 84 euro to 69 euro at very high purity, 95%, 98% carbon dioxide purity. So also here you can see how power consumption change and also how membrane area change depends to membrane property. Also, there are different separation target. So here also you can see the contribution of the capex and opex. So the opex is has more contribution to the total cost. So the second application would be the natural gas. So also the different membrane selectivity and permeance used in the table. We need to, the gas is the mixture of the carbon dioxide and also methane. We feed as 20 bar. We assume we're gonna have at the grid pressure 20 bar. In this case, but I'm not gonna show again sensitive analysis for different applications because of the limited time. But here, only one example is to reach 99% methane recovery and 98% methane purity. So here you see the result, the optimal result the software gives us for natural gas application to achieve our separation target. So the same as the post-combustion, the optimal configuration has 3 membrane stages, but here, instead of inlet gas going to second membrane, is going to third membrane one. And we have also 2 recycled stream from third one to 2 and the second one to first one. We just need to have only 1 vacuum pump in the permeate side of the third one. And at the end, the result is going to be about 12 euro per ton of the natural gas. Gonna be that gonna be cost to achieve our separation target for natural gas separation. Of course, we did the same procedure for natural gas for 2 different membrane, the same separation target. You see again with a bit improvement in the selectivity, the cost going to be reduced from 15 euro per ton to 12.7 euro per ton natural gas. And the last application is the biogas upgrading. You need to increase the purity of the methane from 60% to even 97, 98% to meet the grid specification. So also we estimate our feed pressure is 1 bar. At the end, we are going to reach to 16 bar. So the big difference here is the superstructure give us the 2 stages we need to achieve our separation target at the minimum separation cost. Before I forget, let me tell you here, our optimization is the base of the one of the target was to minimize your gas separation cost. But of course, if you were in our previous webinar, you can also do optimization to have the minimum membrane area. You can also do optimization to have the minimum energy consumption. So it depends to which one is more important to you. But in this case, I'm showing you is only to achieve our separation at the lowest cost, right? So come back to biogas upgrading. So we need only 2 stages. So the first membrane stage here, you see it's removed by structure because the flow going to the first membrane stage was very, very low, very close to 0. So you can ignore it. 2 stages enough for you to achieve 2 stages with only 1 recycled stream. And with 2 vacuum pump, you can reach to your separation target at the minimum cost with about 81 euro per ton biogas. Of course, we did the same for 2 different membrane to see how membrane property can affect our also structure, also the separation cost. So when I did optimization for superstructure for different membrane, for different separation target, not only the capex, opex, this parameter change, but also the whole superstructure change. So here I'll just show you one example. At the end, the main conclusion for this work was, I also show a lot in the previous webinar. Here is starting with the superstructure is the great idea to have a cost-effective configuration for your application, to reduce your membrane cost, to have an efficient process at the lowest energy consumption, you can reach your separation target. So we show how many membrane stages we need based on this fabricated Biocomem membrane, how superstructure look like, how much energy you need to achieve your separation. For example, for post-combustion natural gas, you need to have 3 membrane stages with 2 or 1 recycled stream. Also, but for biogas, you need to have 2 membrane stages to achieve your separation target. Also, we show how it's going to be our separation cost. We also did a comparison to the literature, to conventional technology, to see the comparison between achieving our separation with the Biocomem membrane, how is different compared to other technology, for example, for chemical absorption, adsorption. The more information, more details you can also find in our recent publication. And with this, I would like to thank all of you for listening.
Thank you very much, Rusbe, for showing us the Biocomem activities from the perspective of process design and simulation. I do have a question, although we are a bit behind the schedule already, but I think it's just a thought from my side. We have seen before the point of view of membrane materials and membrane developers, and now we see your perspective from process from process side. What would be your message for the materials developer? Would it be critical at this point to put a lot more effort to improve the performance of the membranes in order to allow, for instance,
Yes.
a decrease in the number of stage and then a decrease in the final cost? How?
Look, first, thanks for the question. Look, we do our best at the end. The main outcome is going to be we fabricate our membrane, develop a membrane, whatever is going to be the carbon membrane or polymeric membrane at the end to separate our gas for depends on our application to achieve our separation target at the minimum cost. So sometimes we can develop a membrane at the cheapest cost, but sometimes we cannot depends to your type of membrane. And another one is to improve your membrane properties, because at the end your main objective is the cost. All this you need to reduce your capex or opex. So sometimes we can do it with the optimize to our process, but at the end we have a limitation for that, both for optimization of the process configuration and also for improving the performance of the membrane. So my point is we need to work in parallel. I mean, not just focus on the improvement of the membrane, not only on focus on the superstructure. So if we work at the same time, both of them, I'm sure we can achieve our separation target. We can produce a membrane. We can have a new novel technology to be competitive compared to the conventional technology available.
Thank you very much.
For example, for partner, they can even a bit improvement in the membrane selectivity. We can easily compete with the available technology in the real industrial application.
Thank you very much. We can then move to our last presentation of the webinar. I give the word to Andrea Randon from TUE that will give a speech on the demonstration activities of Biocomem membranes at TRL 4 and 5. Andrea, the floor is yours.
Share my screen. What you can see?
Yes.
Yeah, okay.
Yes.
So I can start. So demonstration of the Biocomem membranes at TRL4 and TRL5. So first outlook of the presentation. So there will be an introduction, the membrane module modeling, what we have done till now. The setup description for the TRL4 demonstration, the agent tests composition of the different applications, and the procedures for the assessment of the influence of the pollutants over the membrane, and a setup description and results that are coming from DMT, our partner in TRL5. So currently, chemical separations are playing a major role in energy use and in process industry. They often have lower, and because the fact that they often have a low energy consumption, low operational cost, and small footprint, they are easy to scale up and to incorporate into existing technologies. The Biocomem first goals is to produce at pilot scale new bio-based polymers and membranes then that will bring value for 3 different CO2 separation applications, namely the post-combustion flue gas treatment, natural gas sweetening, and biogas upgrading. While for the first application, the aim is for reducing the emissions of CO2. For natural gas sweetening applications, the presence of CO2 affects the quality of the product gas and can potentially form in acids in presence of water. And then you want to remove it. For the gas upgrading application, we want to remove the CO2 in order to for the product stream to gain a bigger heating value. Another goal is to validate at pilot scale an industrial environment in an industrially relevant environment, TRL5, the 3 production processes. Okay. So as you can see from the, now we're going to talk about the modeling. As you can see from the top right of the screen, the figure illustrates a single membrane module operating in concurrent mode with the shell feed side. Referring to this illustration and considering also a system with the N components, the following equation on the left can be written for a single module, where the permeate and retentate quantities must be considered as local properties, differential properties, in function of the axial coordinate, Z. We can then write a finite material balance. Basically, the molar flow rate on the feed side is equal to the summation of the molar flow rate on the retentate and permeate side, and this is also valid for every species contained in the gas mixtures. A differential material balance in which the differential variation in the molar flow rate is equal to the intramembrane flux, so basically the species that are permeating the membrane, times the differential membrane area. We can also define a constitutive flux equation, so the intramembrane flux, which is defined as the permeance time the driving force, so the difference in partial pressure of the component. And then we have the constitution equation, composition equations. The system we are going to elaborate includes 2 times n plus 2 coupled differential equations, and represents the number of the species in the feed gas mixtures, and the input parameters that provide for the boundary conditions include the feed conditions, so the molar flow rate at the feed side, and also the molar fractions of the components at the feed side, and the pressure on the feed side and permeate side, plus the geometrical features of the membrane. Here you can see on the top left the system of differential equations that are describing the permeation behavior inside the membrane module. You can see there is one equation for the variation of the molar fraction of each component on the retentate side and on the permeate side, plus 2 equations describing the variation of the molar flow rate in the retentate side and permeate side due to the permeation. As we were saying before, the initial conditions are the molar flow rate on the feed, the molar fractions on the feed, and the molar flow rate on the permeate side. What we did was also a one-dimensional analysis. So basically, we took the intramembrane flux and we did some algebraic manipulations and introducing some a dimensional parameter that you can see on the left, namely the pressure ratio, the ratio of the permeances, where you can see P1 is always P1 and is given by the fastest component, basic permeance. Then you have the a dimensional molar flow rate and a dimensional area and a dimensional axial coordinate. You can get from this manipulation this formula here, which is the a dimensional intramembrane flux that you can substitute in the system of equation before getting a dimensional system of equation. What we also added was the permeate pressure drop. So we described it through the Hagen-Poiseuille yellow, which is suitable for flow rates in tubes, since the permeate is on the bore side of the membrane for the module. What we should do for achieving the pressure drop was actually calculating the viscosity, which has been calculated from an experimental equation for each single component from the Paris chemical, as you can see in the first formula. And then, since we are treating a multi-component gas permeation model, we applied the Wilke mixing rules. This in the table is you can see below is the validation of this little model for multi-component systems. Then 3-component biogas-like mixtures was used for the model verification. Biogas is a multi-component mixture that contains mainly methane and carbon dioxide with smaller amount of other gases, namely oxygen and nitrogen. Since the common objective for the biogas upgrade is the production of a natural gas substitute, basically, the purified biogas needs to fulfill also the requirements for the supplied natural gas grid. And the natural gas standards usually limit the content of oxygen and nitrogen or these secondary components. So basically, you need to remove them as well. These are the input data taken from Makaruk et al. This publication, which is similar cases to us, except for the length of the membrane module, which in our case is double. What we did was basically assess the performance of the model and see if it was doing what we wanted. Seeing the variation of the partial pressure, as you can see in the figure on the left, versus the dimensional axis position along the membrane. As you can see, the CO2 is the most permeable component, and then the partial pressure is diminishing really fast. And on the other side, you can see the flux of the CO2, the intramembrane flux over L. intramembrane, sorry. From the retentate and permeate side, you can see the retentate in blue and the permeate in orange. And as the driving force is high, the permeate flux is increasing pretty fast. And as it is diminishing, is basically becoming horizontal. So this is what's mainly what we expected also for the applications. So the removal of the CO2. And we also checked for the how was going the partial pressure of the methane versus the adimensional axial position of the membrane and the flux as well. And since during the biogas upgrading, what you want is an enrichment in the retentate side. As you can see, retentate in blue and permeate in orange, the partial pressure of the CO2 along the membrane is actually increasing, which is actually what you expect, basically. We validate also the model with the experimental data. You can see in the two figures, the experimental data are the dots, while the dashed lines represent what the model calculates. And if you see in the figure on the left, the model values are in good agreement with the measured values. Except that they slightly overestimated the methane enrichment. This model, permeation tests are ongoing for the 3 different applications, and the experimental data that we are collecting now will be then treated published later on, not now. It's a pity. And yeah, this model will be then validated also with our experimental data. Now I'm going to describe the setup that we have here, that we build here at the TUE. So as you can see, there is on the left a big feed system. We can create a lot of complex mixtures to test our membranes. And yeah, there are also the pollutants that we need for doing the agent test. And once the mixture is created, is conveyed through the water vapor saturation unit, so the controlled evaporation mixing unit, the SEM. For the SEM, we need to supply the gas mixtures and also the water coming from a demi-water tank, which is pressurized through nitrogen. There's a flow controller. I calculated all the molar concentration, molar fractions that I need to saturate the different components. And then inside here, the stream is saturated and is then sent to the core of the system, which is the membrane module. As you can see on the left here, we have the possibility to use sweep gas as well. The membrane module will separate the mixtures in the retentate on the top and the permeate below. You can see here there are 2 vertical branches. I can spill part of the retentate and permeate and analyze it through a GC that you can see here on below on the right. And there's also a vacuum system that permits to create vacuum and reach higher pressure ratios on the permeate side. Then there is another component in the setup, which is this thermosaturator that has been done for feeding the toluene, since during the agent test we'll be using toluene for the biogas upgrading applications, and we need to find a solution. And what we found is just thermosaturation, which is basically thermosaturator, which is basically a tank in which inside this tank there will be liquid toluene in equilibrium with this vapor. And we found that at ambient temperature, so 20 degrees C, I calculated the saturation pressure of the vapor through the Antoine law. And we see that the ppm that we obtain in equilibrium, if there is a flow flowing inside, it takes an amount of toluene equal to 2,700 ppm. What we need for the agent test is actually the 10% of it. So what we do is send in a flow rate of CH4, so methane in the case of biogas upgrading. That will be the 10% of the total flow rate. And taking away this amount of vapor, we can achieve the composition which is suitable for the accelerated agent tests. So there are 3 different applications in the Biocomem. These are the composition that we chose for the agent test. For the 3 different applications, the first one, natural gas, we chose ethane as representative of the hydrocarbons. There is a composition also for the post-combustion CO2 capture, in which the pollutants are SO2 and carbon monoxide, and it will be saturated around the 20% of molar fraction of water vapor. And this is actually what is stated on the project as a composition, a real composition for the post-combustion case. So it comes from cement kiln production. And then the biogas upgrade, in which the pollutants chosen are the hydrogen sulfide, the ammonia, and as we were saying, the toluene. So the procedure for the membrane degradation assessment, we need to assess how the performance of the membrane is degrading over time while sending a real gas composition. So the first things to do is to establish a synthetic clean gas, which is a representative test condition that is coming from the permeation test, the binary permeation test, that is chosen for each application. This performance reference is used to assess the degradation stability of the membrane. What we do is basically send in first place the synthetic clean gas, assess the performance of the membrane, the separation of the membrane. Then we run agent testing cycles of 24 hours each of the real gas composition, which is chemically attacking the membrane. And then after 24 hours, we send again the synthetic clean gas and we see if the performance we are finding now is worse than the one before basically with the first one. And if it's not too worse, we just repeat the cycle until we reach what we want. Tests with these real composition are meaningful since there's the opportunity to see and study how the membrane reacts to these pollutants and they activate. I'm going to present some of the results that at TRL5 that the team DMT achieved. What they did was basically testing the membranes, and to do that, you can see in blue, you can see it's a full-scale biogas operating unit. There is the digester, then there is the pretreatment, the compression system, and then the membrane separation. So what they did before the tube that is going into the membrane separation, they spill a part of the biogas, of the real biogas. They send it to a test skid, and then they recirculate it inside the same full-scale unit. So what they get is a pretreated real gas with the decomposition, so 50% of methane and 45 CO2, and then minor components. For a flow rate that can range from 2 to 5 normal cubic meters per hour, and the pressure that can range from 1 to 14 bar. What they can do in terms of measuring and controlling, they can control the inlet and outlet flow, the compositions, the pressure, and the temperatures. Then they can assess also from the data they get the performances of the membrane. Here is a picture of the test skid. As you can see on the top, there are tubes of the real plant. They just spill quantities from that. And here you can see the membrane model from head-on. And yeah, this is it. So here are some results that they get for this process condition. They sent like 3 normal cubic meters per hour wet feed at a pressure of 6 bars and an almost ambient temperature, 22 degrees C. What they get is a good enrichment on the right-hand side of methane because they pass from 56 to 80. And a purity of the CO2 on the permeate side of 55. This performance was, as you can see, there is a field and simulation here in the table, and was initially validated by head-on, providing the simulations for the similar exposure conditions, assuming a membrane, not assuming actually, for a membrane area of 0.44 square meters. And yeah, as you can see, they compare quite well with what is coming from the field, except for the values of the permeances here of the CO2 with respect to the simulated one, and for a little difference in also to the latent concentrations of methane. What they use to assess the separation capacity, permeance, and selectivity is for the separation capacity, they use a process formula, actually. This is the number of modules, but once you put one, you can get from the same formula the separation capacity for a single module. And what they did, this is measured in gas permeation unit time square meters. So divided by the membrane area, you can get the permeance and then the selectivities. And here is how they perform the agent tests. They did a degradation test for a total of 240 hours per membrane, with a process condition of 5 normal cubic meters, which was the feed flow rate, at 6 bar. And as you can see, for example, here in the permeances, here are how it is assessed, basically the degradation, and you can see that the permeant of the CO2 is decreased up to 26%. Thank you all. This is it.
Thank you very much, Andrea, for giving also an overview about what is happening from demonstration perspective within the Biocomem project. Yeah, we can see also, like, from your PNID and the methodology that you have shown for testing at lab scale, the presence of a lot of impurities is crucial to finally assess the performance of these membranes. But and maybe like a question, maybe not only for you, but also for other speakers, particularly the membranes developers, would be like what is the expected actual deactivation of these membranes due to both organic and inorganic impurities? Are also the data that Andrea has shown from the DMT plant, say, are reference in this respect, this minus 10-25% after 24 hours? Is it something that we can use already as a strong reference?
So maybe I can say something from our experience. So we are developing polyactive membranes since 2005, and now we are coming to practical application. Last 10 years, we are studying this membrane in different processes on coal-fired power plants, on lignite or hard coal. Now we have the machine on power plant which is fed by wood. And so we understand what actually we are separating. The main thing is the gas should be prepared for the separation. So you need to knock out as much water as it possible. You need to get rid of different impurities like NOx, SOx, it's better. And you should not allow any condensation on the membrane surface. After this, you can separate, and membrane actually performs quite well. We have evidence that membrane is working in one separation unit for something like 5 years, and with multiple start and shut down of the system. And in coal-fired power plant, it works as well, quite well. We have published this data before.
Okay. Thanks for this comment based on your important experience in the field. And then, if there are no other questions, maybe I would like to ask Oana if she, as a coordinator, has some final words regarding the project.
Yes, thank you very much. Thank you very much for organizing this webinar. It was really nice to be able to share our results, especially that in the project we could not disseminate many interesting results because we wanted to have some patents before that. And this week on Tuesday, we managed to fill in a few of them. So this is why today we could have nice content, technical content for the presentations. There are many things we didn't show. It was not possible in a webinar after 3.5 years of project. What we didn't mention was prototype C, the complete bio-based. We also have many results there. It's something that we couldn't share as well because of time restrictions. But now to wrap it up, we are actually having many more things to do in the future based on these results. And yeah, it's like connecting chemical synthesis with from the monomer side to the final membrane in 3.5 years. I think we did manage to have very nice results in the end, but it's still a lot of things we can do in the future.
Great. I do agree with this analysis. And I think that we had a nice demonstration during these 2.5 hours this morning. So once again, I would like to thank all the speakers for their nice presentations and discussions. And with this, I think that we can conclude the webinar. I just remember you again that the recording will be available, and just follow us on LinkedIn to have the link. But anyway, the recording will be placed on YouTube. And we'll see also for the slide, many partners have already said yes, they are also going to be available. But yeah, I will check also with the full portfolio of speakers if they are willing to do so. And so said, thank you again, everyone, and yeah, have a nice rest of the day.
Thank you. Thank you very much.
Thank you, everyone.
Bye bye.
Yeah,
Bye.
thank you. Bye.